It's Daddy Cause again, and in this video we'll be talking about oxygen. In the last video we looked at hydrogen, but in this video we're looking at oxygen. Oxygen was discovered first by Wilhelm Scheele in 1772, Carl Wilhelm Scheele, in that year, and it was Antoine Lavoisier also that named oxygen as oxygen in 1775, meaning acid former. At that time, Lavoisier wrongly thought that oxygen is present in all acids. That was why he named oxygen as acid former. Oxygen belongs to the group 6 of the periodic table, and in fact the first element in that group, and that's configuration 1s2, 2s2 and 2p4. Oxygen exists in allotropic form, and there are two major allotropes of oxygen. First and foremost, what is the meaning of allotropy? Allotropy is the existence of an element in different forms in the same physical state. That is allotropy. Consider the principal of your school. For example, when he or she comes to school, is a principal. But when he gets home, he becomes a father to somebody, becomes an husband to the wife. And if that principal happens to be a pastor, an imam, or a religious leader, when he gets to the church or to the mosque, he assumes another status. Only one man existing as a principal, as a pastor, as a father, as a husband. That is what we mean by allotropy. The way you are going to see the principal in school, the way he will be acting, is not the way we act at home, and not the way we act in the church. So, some elements also exhibit these characteristics such that they exist in different forms but in the same physical state. You call that allotropy, the existence of an element, one element in the same physical state but in different forms. What are allotropes? Allotropes are those different forms that an element exists in the same physical state. For example, oxygen exhibits allotropy, that is, oxygen has allotropes. And there are two major allotropes of oxygen. We have the molecular oxygen, which is O2, the one that you have on your screen. And we also have ozone, which is O3, the one you also have on your screen. So this is ozone, trioxygen, and you also have oxygen itself, molecular oxygen, dioxygen, O2. So these are the two allotropes of oxygen. We have some other elements that exhibit allotropy. Examples are sulfur. Sulfur has rhombic and monoclinic sulfur, and they are very different when you are looking at them, but they are made up of the same element. They are both sulfur, both rhombic and monoclinic. Diamond and graphite also are allotropes of carbon. If you see diamond and you see graphite, you won't easily know that they are from the same element because they have very different appearances. So, but you can always test or confirm if two different substances are from the same element by combustion. For example, if you burn diamond in oxygen, it gives you CO2 as the only product. If you burn graphite also in oxygen, it gives you CO2 as the only product. This tells you that both diamond and graphite are actually elements of carbon. So that's how you quickly know, and you can confirm like that. Not only sulfur and carbon that are exhibiting allotropy, We also have some other elements that exhibit allotropy. Phosphorus has 3 allotropes: white phosphorus, red phosphorus, and black phosphorus. Tin, we have white tin and we also have grey tin, as you can see on your screen. What are the properties, physical properties of oxygen? You know, when I talk about physical properties, I told you under hydrogen that we're referring to solubility, we're referring to color, we're referring to odor, we're referring to taste, and all those properties that does not require changes in the chemical composition of the substance. For example, oxygen rather is colorless, is odorless, and is tasteless. And the boiling point of hydrogen is minus 183 degrees Celsius. It boils at that temperature and it solidifies, it turns to solid oxygen at minus 225 degrees Celsius. Come again, oxygen boils at minus 183 degrees Celsius and it solidifies at minus 225 degrees Celsius. So any temperature lower than minus 225, oxygen is existing as a solid, and above 183, minus 183, oxygen exists as a gas. So in between those two temperatures, oxygen is a liquid. Next, oxygen is slightly denser than air. Even though it's slightly denser, the density is approximately that of air. The density of oxygen is 16. The density of air is 14. So because of that, you don't normally collect oxygen by displacement of air because their density is approximate. Then oxygen exists as a diatomic element at room temperature. It exists as O2 with a double bond in between the two oxygen, as you can see from the screen. Oxygen joined by a double bond. That's oxygen at room temperature. Then oxygen is sparingly soluble in water. The word sparingly means it's slightly soluble in water. It does not dissolve very well, maybe about 25% or less than that will dissolve in that water. That's sparingly soluble. And those little dissolved oxygen is what the aquatic organisms normally use for their day-to-day activity. The same oxygen is neutral to litmus. It's neither acidic nor alkaline. It's neutral to litmus. How do we test for oxygen? You use a glowing splint. Don't forget, for hydrogen we use a lighted splinter and it makes a pop sound. But in this case of oxygen, we use a glowing splint. A glowing splint is a substance that is almost burning but not yet burning. Tendency to burn, like a charcoal that is hot, red hot charcoal is a glowing splint. Like a cigarette that has been lighted, it's a glowing splint. Look at the one you have in this place. You will see that this wood is almost burning. You can see that it's almost burning. Check the wood, it's almost burning. This is a glowing splint. Is a glowing splint. When you put a glowing splint inside a gas jar that contains oxygen, the glowing splint will catch fire. That means oxygen is present inside that gas jar. You call that rekindling of a glowing splint. So oxygen normally rekindles a glowing splint. So that is the test for oxygen. If you insert a glowing splint inside a gas jar that you suspect it contains oxygen, if that glowing splint is rekindled, if fire breaks out from that glowing splint, then the gas jar contains oxygen. Now, the issue with this test is that there's one other gas that normally rekindle a glowing splint. and the gas is nitrogen 1 oxide. You call this gas a laughing gas. Nitrogen 1 oxide. The formula is N2O. That's nitrogen 1 oxide. It also shows the same results like oxygen. But you can easily differentiate between oxygen and nitrogen 1 oxide using both their physical properties and their chemical properties. For example, physically, oxygen is odorless. It doesn't produce odor. But nitrogen 1 oxide has a pleasant smell. It has a nice smell. 2. Oxygen is slightly soluble in water. That is, about 25% of it is what will dissolve in water. But nitrogen 1 oxide is fairly soluble. That is, it is significantly soluble. About 75% of it dissolves in water. So, these are the ways you can distinguish between oxygen and nitrogen 1 oxide using their physical properties. So, if a gas is odorless and rekindle a glowing splint, it is going to be oxygen. But if a gas has a pleasant smell and rekindle a glowing splint, it is not oxygen, it's nitrogen 1 oxide. Take note of that. You can also distinguish between the two of them by using their chemical properties. Number 1, oxygen reacts with nitrogen 2 oxide, NO. That's NO. So it reacts with nitrogen 2 oxide, NO, to give you a brown gas called nitrogen 1 oxide, NO2. So if you pass nitrogen 2 oxide, that's NO, into a gas that contains oxygen, the color of the gas will turn to brown. That means oxygen is present there. Oxygen can react with nitrogen 2 oxide, but nitrogen 1 oxide cannot react with oxygen. This does not react with NO. No reaction at all. But oxygen can react with NO and give you a brown gas, NO2. So take note of that. Then secondly, oxygen reacts with hot copper without producing a residual gas. When oxygen reacts with hot copper, it gives you a solid, copper 2 oxide, black solid. However, in the case of nitrogen 2 oxide, when it reacts with hot copper, it gives you CuO and produces another gas, N2. So this is a residual gas that will be formed. But in the case of oxygen, you don't form a residual gas when it reacts with heated copper. But nitrogen 2 oxide forms a residual gas with heated copper. So this is how you distinguish between oxygen and nitrogen 2 oxide whenever the gas rekindles a glowing splint. How do you prepare oxygen in the laboratory? There are 2 methods you can use. Number 1, you can use thermal decomposition of potassium triacylchlorate 5, KClO3. Secondly, you can use catalytic decomposition of hydrogen peroxide. So those 2 methods can generate oxygen. And if you take note, both compounds contain sufficient amount of oxygen atoms. Number 1, how do we prepare oxygen from the composition of potassium triacylchlorate 5, KClO3? You put the potassium triacylchlorate 5 inside a test tube like this, or a flask, boiling tube rather, not test tube, boiling tube. Boiling tube is thicker and can withstand higher temperature. So you are going to put manganese 4 oxide as a catalyst to enable the decomposition to be very fast. So when you do that, the KClO3 will decompose into KCl and oxygen atoms, oxygen molecule rather. So 2 mole of KClO3 will produce 2 mole of KCl and 3 mole of oxygen atoms. So that oxygen can be collected over water. Remember that oxygen is insoluble in water, so you can is sparingly soluble in water, so only few will dissolve in water. Majority of the oxygen will not dissolve in water. So that's how you collect oxygen from KClO3. You can use this method in the laboratory. Get your boiling tube. This is your boiling tube. Heat KClO3 with MnO2 catalyst. When you do that, oxygen gas will come out, and you collect it by displacing water or collect it over water. So that's what you do there. Next, you can produce it from hydrogen peroxide decomposition. Put your hydrogen peroxide inside the round bottom flask. Ordinarily, without touching it, H2O2 will decompose by itself into oxygen following this chemical equation. H2O2 is supposed to be H2O2, not H2O. H2O2, when you eat it or even leaving it alone, will give you water and oxygen gas. But if you want the reaction to be very fast, you can use a catalyst to aid the decomposition. Manganese 4 oxide catalyst. That's why you see it here. So it makes the oxygen gas to come out very fast and very quickly. So don't forget, this is your test-tube funnel. For the hydrogen peroxide is a liquid. Put your MnO2 is a solid inside the round bottom flask. Then drop it inside. As the H2O2 is touching the manganese 4 oxide, oxygen is produced, and you collect it over water in this place. If you want to collect oxygen dry, you are not going to use air, because oxygen has approximate density like air. So what you can do is you use mercury instead of air. So you put mercury inside a gas jar. You know, mercury is a liquid, so but not having water. So once the oxygen gas is being produced, so instead of putting water here now, you can put mercury there. So you can put mercury in this place. So when the oxygen gas is coming, oxygen will come and collect over the mercury, and that will be a dry oxygen gas. So you collect a dry oxygen gas over mercury. So that's how you collect oxygen in a dry form. And this will be the end of this video, talking about properties of oxygen and the preparation of oxygen in the laboratory.